The afternoon sun beat down on the captured American tank sitting in the test yard outside Yokohama, its olive drab paint blistered and scorched from battle. Lieutenant Commander Hara Masao circled the vehicle slowly, one hand trailing along the thick steel hull. He had spent the morning firing Japan's best anti-tank weapon at this machine from progressively closer ranges. The results sat in a folder under his arm, numbers that would change everything the Imperial Japanese Army believed about armored warfare. It was late 1944, and for the first time, Japanese military engineers had gotten their hands on an intact M4 Sherman medium tank. Not photographs. Not fragments collected from bombed-out wrecks. An actual, functioning example of the machine that had been dominating every theater where American and Japanese forces clashed. The tank had been captured in the Philippines during the desperate fighting around Leyte, dragged back to a transport ship, and shipped home to Japan for comprehensive evaluation. What Hara and his team discovered in the weeks that followed would shatter every assumption the Japanese military-industrial complex had made about modern armored warfare. The story of this evaluation is not simply about one tank versus another. It is the story of two completely different philosophies of war colliding in steel and rivets. It reveals the moment when Japanese engineers, trained in the doctrine of spiritual superiority and tactical brilliance, confronted the overwhelming material reality of American industrial power. And it demonstrates how technological surprise works not through exotic wonder weapons, but through the systematic application of resources that one side assumed the other could never muster. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand what shocked the Japanese engineers about the Sherman, we must first understand what they expected to find. By 1944, Japan had been building tanks for nearly 2 decades. The Imperial Japanese Army's approach to armored vehicle design had been shaped by specific battlefield experiences and constrained by specific industrial limitations. Japanese tanks were not built to fight other tanks. They were built to support infantry attacks against fortified positions, to break through enemy lines, and to terrify opponents who had never seen mechanized warfare before. The Type 97 Chiha medium tank, Japan's most widely produced armored vehicle, embodied this philosophy perfectly. Introduced in 1937, the Chiha was designed for operations in Manchuria and China, where the enemy rarely fielded tanks and almost never had effective anti-tank guns. It weighed approximately 15 tons, carried a crew of 4, and mounted a Type 97 57mm gun in its turret. By the standards of the late 1930s, this was a respectable combat vehicle. It could advance with infantry, suppress machine gun positions, and destroy bunkers. Against the Chinese armies Japan faced on the mainland, it was adequate. Against the Soviet tanks encountered at Khalkhin Gol in 1939, it was revealed to be dangerously inadequate, but that lesson had been imperfectly absorbed. The Chiha's armor thickness tells us everything about what Japanese designers prioritized. The front hull armor measured approximately 25 mm at its thickest point. The turret armor was similar. The side and rear armor was substantially thinner, sometimes as little as 12 mm. This was armor designed to stop rifle bullets and shell fragments, not armor-piercing projectiles from dedicated anti-tank weapons. The trade-off was intentional. Thin armor meant lighter weight. Lighter weight meant the tank could be transported on Japan's underdeveloped road network, could cross bridges designed for civilian traffic, and could be shipped to the Pacific Islands where much of the fighting now occurred. It also meant the tank could be built quickly and cheaply, using Japan's limited steel production capacity. The power plant of the Chiha was a Type 97 inline 6-cylinder diesel engine producing approximately 170 horsepower. This gave the tank a maximum road speed of about 38 km per hour under ideal conditions. Actual cross-country speed was considerably slower. The engine was reliable by Japanese standards, which meant it frequently required maintenance, but could be repaired by moderately trained mechanics using hand tools. The transmission was a manual gearbox, requiring significant physical effort from the driver. Everything about the Chiha's design emphasized simplicity, manufacturability, and ease of field maintenance over raw performance. By 1942, when Japan entered full-scale war with the United States and the British Empire, the inadequacies of this design philosophy were already becoming apparent. American Stuart light tanks encountered in the Philippines proved difficult for Japanese tank crews to engage effectively. British tanks in Burma and Malaya demonstrated superior armor protection, but the Japanese military-industrial establishment was not structured to respond quickly to these lessons. Japan's industrial capacity was already stretched thin, supporting the Navy's needs, maintaining the air forces, and producing the vast quantities of rifles, machine guns, artillery pieces, and ammunition required by a multi-front war. Redesigning and retooling for new tank production was not a priority. Instead, Japanese engineers focused on incremental improvements. The Type 97 Chiha was upgunned with a 47mm high-velocity weapon in the Shinhoto Chiha variant, giving it improved anti-armor capability. The Type 1 Chihei medium tank, introduced in 1943, featured modestly thicker armor and a more powerful engine, but it was produced in tiny numbers. The Type 3 Chinu, designed specifically as a tank destroyer to counter American armor, mounted a 75mm gun derived from an anti-aircraft weapon. Only about 60 of these were ever built, and none saw combat before the war ended. Japan was fighting the Pacific War with tanks designed for the war in China, and everyone involved knew it. The Japanese Army's tank doctrine further reveals the gulf between Japanese and American approaches to armored warfare. Japanese tactical manuals emphasized the offensive spirit of the tank crew, the importance of aggressive action, and the value of surprise and initiative over firepower and protection. Tanks were to be used in mass wherever possible. But mass, in Japanese terms, meant companies of 10 to 15 vehicles, not the battalion and brigade-sized formations the Soviets and Americans deployed. Tank versus tank combat was acknowledged as a possibility, but not treated as the primary mission. The assumption was that Japanese tanks would primarily face enemy infantry, and that enemy tanks, if encountered, could be dealt with through superior crew training, tactical cunning, and the spiritual strength of the Japanese soldier. This assumption was not entirely baseless. In the early years of the Pacific War, Japanese tank crews had achieved some notable successes. At the Battle of Slim River in Malaya in January 1942, Japanese tanks broke through British defensive positions in a rapid nighttime advance that captured or destroyed significant quantities of British equipment and led to a general retreat. In the Philippines, Japanese armor contributed to the successful advance down the Bataan Peninsula, but these victories occurred against opponents who were themselves poorly equipped, inadequately trained in anti-tank defense, and often surprised by the speed and aggression of Japanese combined arms tactics. They were not victories against modern, well-equipped armored forces backed by industrial economies operating at full war production. The engineers who gathered around the captured Sherman in late 1944 understood all of this context. They knew Japanese tanks were outclassed. What they did not know was by how much, or in precisely what ways. The Sherman sitting in the test yard represented an opportunity to answer those questions with empirical data, rather than battlefield reports filtered through the fog of war. It was an opportunity to measure, weigh, test, and understand exactly what the Americans were fielding, and it was an opportunity that came far too late in the war to change anything, but which would reveal truths that could not be ignored. The M4 Sherman medium tank that Japanese engineers examined was not an exotic prototype or an experimental model. It was a standard production vehicle, one of approximately 50,000 Shermans manufactured by the United States between 1942 and 1945. This ordinariness was itself significant. The Sherman was not rare. It was not special. It was what America produced in vast quantities and shipped across 2 oceans to fight on every continent where the war raged. Understanding the Sherman meant understanding American industrial power made manifest in steel. The tank captured in the Philippines was most likely an M4A, one variant, identifiable by its cast rather than welded hull. This variant was produced primarily by the Lima Locomotive Works, the Pressed Steel Car Company, and the Pacific Car and Foundry Company. The choice to examine casting marks, manufacturers' plates, and production details would have been among the first tasks the Japanese engineers undertook. These details revealed not just what the Americans had built, but how they built it. The cast hull construction indicated access to enormous casting facilities, sophisticated metallurgical expertise, and quality control systems that could ensure consistency across multiple production facilities. These were not capabilities Japan possessed at comparable scale. The first shock came when engineers measured the armor thickness. The Sherman's front hull armor measured approximately 51 millimeters at an angle, providing effective protection equivalent to roughly 75 millimeters of vertical armor due to the slope. This was nearly 3 times the effective thickness of the Chiha's frontal armor. The turret armor measured 76 millimeters at the front. Even the side armor, often the most vulnerable point on any tank, measured 38 millimeters. The Americans had built a tank where even the weak points were better protected than the strong points on Japanese designs. But thickness alone does not tell the complete story. The quality of the armor plate mattered just as much as its thickness. Japanese engineers subjected samples of Sherman armor to metallurgical analysis. What they found was steel of exceptional quality and consistency. The face-hardened armor showed proper heat treatment throughout. There were no significant inclusions, no obvious weak points in the metal structure, no evidence of the kind of manufacturing shortcuts that characterized late-war Japanese armor production when steel quality had become increasingly suspect. This was not just thick armor. It was properly made thick armor, produced by an industrial system that still had access to high-quality raw materials and could maintain production standards even while manufacturing tens of thousands of vehicles. The testing protocol was methodical. Engineers positioned Japanese anti-tank weapons at various ranges and fired at the Sherman's hull and turret. They used the Type 1 47mm anti-tank gun, the most effective dedicated anti-armor weapon in Japanese service. At 500 meters, the standard engagement range for which the gun had been designed, the armor-piercing rounds bounced off the Sherman's frontal armor. They penetrated the side armor but without the kind of catastrophic spalling and damage that would guarantee a kill. At 300 meters, results improved marginally, but the Sherman's frontal armor remained largely impenetrable to the Japanese gun-firing standard ammunition. The implications were carefully noted in the evaluation reports. A Japanese tank crew encountering a Sherman in combat would need to maneuver to get a side or rear shot, would need to close to point-blank range, or would need to score a lucky hit on a vulnerable component like the tracks or vision blocks. The Sherman crew, meanwhile, could engage from any angle at any range their gun could reach. The Americans had built a tank that could simply ignore most of what Japan could throw at it. The examination of the Sherman's main armament was equally revealing. The M375mm gun mounted in the tank's turret was a weapon of entirely different capability than anything Japan fielded in an operational tank. The gun could fire multiple types of ammunition: high-explosive shells for anti-infantry and anti-structure use, armor-piercing solid shot for anti-tank work, and specialized rounds for specific tactical situations. The ammunition stowage inside the Sherman held 90 rounds, suggesting American logistics could keep these tanks supplied even during extended operations far from base. The Type 97 57mm gun on the Chiha carried, by comparison, 120 rounds of a less powerful projectile. Japanese engineers test-fired the Sherman's gun at a captured Chiha positioned at various ranges. The results were not surprising but were still sobering to document officially. At 1,000 meters, the Sherman's armor-piercing shot punched completely through the Chiha's frontal armor, through the fighting compartment, and out the rear. At 1,500 meters, the performance degraded only marginally. The Sherman could destroy any Japanese tank from ranges at which Japanese tanks could not even effectively engage the Sherman. This was not a question of crew skill or tactical doctrine. This was pure material superiority, measurable in millimeters of penetration and meters of effective range. The power plant examination provided another set of revelations. The Sherman's engine was a Continental R, 975 radial aircraft engine, air-cooled, producing approximately 400 horsepower. This was more than twice the power output of the Chiha's engine. But raw horsepower was not the only difference. The American engine was smooth, well-balanced, and featured sophisticated carburation and ignition systems. It started reliably in cold conditions and ran for hundreds of hours between major maintenance. The Japanese engineers documented the quality of the engine bearings, the precision of the machining, and the accessibility of maintenance points. Everything about the engine design spoke to an industrial system with mature manufacturing capabilities and no shortage of skilled machinists. The transmission further illustrated American engineering priorities. The Sherman used a controlled differential system that allowed relatively easy steering. The driver operated levers that could brake individual tracks, assisted by a power system that reduced the physical effort required. The controls were designed for operation by soldiers with modest training. The Japanese transmission systems, by contrast, required significant upper body strength to operate and were notorious for being difficult to use under combat stress. The American approach was to engineer the difficulty out of the system. The Japanese approach had been to train the difficulty out of the soldier. When both systems worked, they could both accomplish the mission. When systems failed or soldiers became exhausted, the American design proved more forgiving. The suspension system provided yet another contrast in design philosophy. The Sherman used a vertical volute spring suspension system, or VVSS, with each bogie featuring a pair of road wheels mounted on a vertical volute spring assembly. This suspension was not particularly sophisticated by the standards of later war tank design. The Soviets had better suspension systems. The Germans had better suspension systems. But the Sherman's suspension was robust, easy to maintain, and could be repaired in field conditions with standard tools and replacement parts that were, according to the documentation found inside the tank, readily available through American logistics networks. Japanese engineers noted the interchangeability of components. Road wheels could be swapped between positions. Track links were standardized and could be replaced individually. Spare parts were stowed in accessible locations on the tank's hull, and the parts were clearly labeled. The American approach was to assume things would break and to make repair as straightforward as possible. The Japanese approach had been to build things as cheaply as possible and to expect that repair would happen at depots when vehicles were pulled from the front lines. The Sherman was designed to be maintained by its crew. The Chiha required specialist mechanics for most repairs beyond the most basic. The examination of the Sherman's interior revealed differences that went beyond mere engineering. The fighting compartment was spacious compared to Japanese tanks. The crew of 5 had defined positions with adequate room to perform their duties. The commander had a cupola with vision blocks providing a 360-degree view. The gunner had a telescopic sight and a periscope. The loader had space to handle ammunition efficiently. The driver and assistant driver sat in a relatively comfortable forward compartment with adequate visibility and ergonomic controls. Everything about the interior layout suggested that the Americans had considered crew efficiency, crew comfort, and crew survivability as design priorities. Japanese tank interiors, by contrast, were notoriously cramped. Crew members worked in confined spaces with limited visibility. The commander often had to serve as the loader for the main gun, dividing his attention between tactical command and ammunition handling. The idea that a tank should be designed around the comfort and efficiency of the crew was not entirely foreign to Japanese engineers, but it had been subordinated to other priorities: lower weight, smaller target profile, cheaper construction, faster production. The Sherman showed what happened when an industrial power decided that crew effectiveness was worth the extra cost in materials and manufacturing complexity. The electrical systems revealed another dimension of American industrial capacity. The Sherman had an electric turret traverse system, allowing the gunner to rotate the turret smoothly and rapidly using a power motor. Japanese tanks relied on manual traverse, with the gunner physically cranking the turret around using a hand wheel. The electric system was faster, more precise, and less physically tiring. It allowed the Sherman to acquire and engage targets more quickly than Japanese tanks could, particularly when the turret needed to traverse through large angles. The electrical generator, the motors, the wiring, the switches, all of these components represented manufacturing capabilities and design sophistication that Japan simply did not possess in its tank production. The radio equipment found in the Sherman was perhaps the most psychologically jarring discovery. The tank was equipped with an SCR-508 radio set, providing voice communication between tanks and with supporting infantry. The radio was standard equipment. Every Sherman had one. Japanese tanks, with rare exceptions, did not carry radios. Communication between Japanese tanks in combat relied on signal flags, hand signals, or pre-arranged tactical plans that crews executed without real-time coordination. The commander of a Japanese tank company could not talk to his platoon leaders once the attack began. The commander of an American tank company could coordinate his entire force, respond to changing tactical situations, and call for support from artillery or aircraft, all while moving and fighting. The implications of this difference extended far beyond mere tactical convenience. The radio revealed a fundamental truth about American military doctrine. The Americans assumed that battlefield situations were too complex and too fluid to be managed by rigid pre-battle plans. They assumed that junior leaders would need to make decisions and communicate those decisions to their superiors and their peers. They assumed that the chaos of combat required constant information flow to be managed effectively, and they had built a tank and an entire tactical system around that assumption. The Japanese assumption had been nearly the opposite, that detailed planning, spiritual preparation, and disciplined execution of orders would overcome the friction of battle. The Sherman's radio set represented a different theory of how modern war actually worked. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The logistical evidence found in and around the captured Sherman added another layer to the Japanese engineers' understanding. The tank came with comprehensive technical manuals, maintenance schedules, and parts diagrams. These documents were printed in clear English with detailed illustrations, suggesting a logistics system that assumed tank crews and maintenance personnel needed ready access to technical information. The manuals covered everything from basic operation to complex repair procedures, and they were written for soldiers with high school educations, not for engineers with university degrees. The spare parts stowage and the inventory lists found in the tank's documentation revealed the scale of American logistics. The Sherman carried spare track blocks, spare bogie wheels, spare tow cables, tools, track tension adjustment equipment, cleaning supplies for the gun, oil and lubricants for the engine, and a host of other maintenance items. The inventory suggested that American logistics planners assumed tanks would operate far from supply depots for extended periods and needed to be as self-sufficient as possible. Japanese tanks carried far fewer spare parts, operating under the assumption that supply lines would remain open and that damaged vehicles could be pulled back to depots for repair. But it was the quality and quantity of the stored supplies that truly shocked the Japanese evaluation team. The food rations found in the Sherman included canned meat, canned fruit, chocolate bars, cigarettes, coffee, and other items that Japanese soldiers would have considered luxuries. The sheer variety and caloric density of American field rations indicated a logistics system that could provide frontline soldiers with nutrition that sustained not just survival, but actual physical performance. Japanese soldiers in the Philippines were, by late 1944, often on reduced rations, sometimes literally starving. The idea that the enemy could keep frontline armoured units supplied with abundant, high-quality food while operating thousands of kilometres from the continental United States demonstrated a logistical capability that defied Japanese assumptions about what was possible in modern war. The psychological impact of these discoveries on the Japanese engineering team cannot be understated. These were not naive men. They understood that America was a wealthy industrial power. They understood that Japan's industrial capacity was limited compared to the United States, but understanding something abstractly and confronting it as physical evidence are entirely different experiences. The Sherman was not a superior weapon in the way that a samurai sword is superior to a club. It was superior in the way that a factory is superior to a workshop. It represented systematic advantages in materials, manufacturing, design, logistics, and doctrine that could not be overcome by courage, clever tactics, or spiritual strength. Lieutenant Commander Hara Massao's final report on the Sherman evaluation was a masterpiece of careful technical writing that barely concealed its devastating implications. He documented every measurement, every test result, every component analysis. He compared Japanese and American capabilities point by point, always using neutral, factual language. But the conclusion was inescapable. Japan could not build tanks like the Sherman, could not support tanks like the Sherman, and could not defeat tanks like the Sherman with existing Japanese equipment. The material gap was not merely significant, it was, for practical purposes, insurmountable. The report circulated through the Imperial Japanese Army's technical services in early 1945. Copies reached the Army Ministry, the General Staff, and various planning departments. The response was complicated. No one disputed the facts Hara had documented. No one suggested his analysis was incorrect. But the implications of accepting his conclusions were too vast to process in any actionable way. Japan was already losing the war. The Navy had been shattered at Leyte Gulf. American bombers were beginning to systematically destroy Japanese cities. The Soviets were massing forces in Manchuria. The idea that Japan also faced insurmountable material inferiority in ground combat was simply one more unbearable truth to be acknowledged and then, for lack of any alternative, ignored. Some officers argued that the Sherman's superiority did not matter, because the final battle for Japan would be fought differently. Japanese forces would not meet American tanks in open combat, where the Sherman's advantages in armor, firepower, and mobility could be fully exploited. Instead, Japanese defenders would fight from fortified positions, use terrain to negate American advantages, and employ suicide tactics, where a single soldier with an explosive charge could destroy a tank regardless of its armor thickness. This was not an entirely unreasonable argument. Japanese forces in the Philippines, on Iwo Jima, and on Okinawa did inflict significant casualties on American armor using exactly these tactics. But it was an argument born of desperation, not confidence. It was the logic of a force that knew it could not win but hoped it could make victory too expensive for the enemy to pursue. Other officers focused on the few areas where Japanese designs showed some advantages. The Chiha was lighter than the Sherman, making it easier to transport by sea and more suitable for operations on Pacific islands with limited infrastructure. The diesel engine of Japanese tanks was less flammable than the gasoline engines in Shermans, reducing the risk of catastrophic fires when penetrated. Japanese tanks were simpler, requiring less sophisticated maintenance and being easier to repair with limited tools and spare parts. These advantages were real, but were overwhelmed by the Sherman's superiority in virtually every other category. It was like praising a rowboat for being easier to beach than an aircraft carrier. The deeper issue that the Sherman evaluation exposed was not about tanks specifically, but about Japan's entire approach to industrialized warfare. The Sherman was not a wonder weapon. It was not even, by the standards of 1945, a particularly advanced tank. The Germans had Panthers and Tigers that could destroy Shermans with ease. The Soviets had developed the T-34-85 and would soon field even more capable designs. But the Sherman was producible in vast quantities, supportable across global supply lines, and good enough to accomplish its mission against most opposition. It represented the American theory of victory. Build equipment that was reliable, maintainable, and adequately effective. Then produce it in such overwhelming quantities that material superiority compensated for any individual performance shortcomings. Japan had never fought a war this way, and fundamentally could not. Japanese industry in 1944 was producing approximately 1,200 tanks per year across all types. American industry was producing over 2,000 Shermans per month, plus thousands of other armored vehicles. The ratio was not 10-1 or even 20-1 in specific categories. The overall ratio of American to Japanese armored vehicle production during the war years was approximately 40-1. Japan could have designed a tank superior to the Sherman, in fact. They tried several times in the late war period, but they could not have built it in meaningful numbers, could not have supported it in combat, and could not have replaced losses at anything approaching the rate at which losses would occur. The engineers who examined the Sherman understood this. Their reports danced around the implication, but it was there in every line of analysis. Japan was not losing the tank war because Japanese tanks were poorly designed, though they were. Japan was losing because Japan could not compete industrially with the United States, could not match American resource extraction, could not replicate American manufacturing capacity, and could not sustain the logistical networks required to keep modern armored forces operational across the vast distances of the Pacific War. The Sherman was proof of this disparity made tangible. In the spring of 1945, as American forces prepared for the invasion of the Japanese home islands, Japanese planners studied the Sherman evaluations and tried to devise countermeasures. They stockpiled anti-tank mines. They prepared fortified positions with interlocking fields of fire designed to trap American armor in kill zones. They trained soldiers to attack tanks with satchel charges and magnetic mines, accepting that these tactics would be suicidal, but arguing they would be effective. They moved their remaining tanks into positions where they could ambush American forces, hoping to use terrain and surprise to offset their material disadvantages. All of these measures were reasonable within their context, but they were measures designed to slow defeat, not to achieve victory. The captured Sherman sat in the Yokohama test yard through the spring and into the summer of 1945. Engineers continued to use it for various tests, measuring fuel consumption, testing track durability, evaluating the effectiveness of various camouflage schemes. In early August, American bombers hit the facility during a raid, and the Sherman was damaged beyond repair by bomb fragments and fire. It was a fitting end for a machine that had travelled so far to reveal so much. The Sherman had been captured as a trophy, studied as a puzzle, and had become evidence of a truth no one wanted to acknowledge. After Japan's surrender on August 15, 1945, American occupation forces discovered some of the technical reports on the Sherman evaluation. These documents were collected along with vast quantities of other Japanese military records and shipped back to the United States for analysis. American intelligence officers found the reports interesting, but not particularly surprising. They confirmed what American tankers already knew from combat experience. The Sherman was superior to Japanese tanks in virtually every measurable way. What the Americans found more interesting was what the reports revealed about Japanese thinking, about the assumptions and doctrines that had shaped Japanese military preparation. The Japanese engineers who conducted the evaluation survived the war and went on to varying careers in the Reconstruction period. Lieutenant Commander Hara Masao returned to civilian life and worked in the automotive industry, applying some of what he had learned from examining the Sherman to the design of commercial trucks and buses. He rarely spoke publicly about his wartime work, but in private conversations with colleagues, he would sometimes reflect on the Sherman evaluation. What stayed with him was not the technical details, but the moment of realization, the point at which all the measurements and tests cohered into a clear picture of just how vast the gap had been between Japanese and American industrial capacity. He had known intellectually that America was powerful, but the Sherman made that power real in a way that statistics never could. The story of Japanese engineers testing captured Shermans is not a story with a conventional dramatic arc. There is no last-minute reversal, no clever innovation that closes the gap, no moment of triumph over adversity. It is a story about the moment when hope confronts reality, and reality wins. The engineers went into their evaluation hoping to find weaknesses they could exploit, vulnerabilities that could be targeted, design flaws that could be turned into tactical advantages. What they found instead was a machine that worked, that was built by an industrial system that could produce tens of thousands of such machines, and that represented a level of material commitment to warfare that Japan simply could not match. This reality had been apparent to careful observers much earlier in the war. Japanese naval officers who studied American industrial capacity before Pearl Harbor had tried to warn their superiors that a long war with the United States would be unwinnable. They had been overruled by those who believed spiritual strength and tactical brilliance could overcome material disadvantages. The Sherman evaluation in 1944 provided detailed, undeniable proof that the pessimists had been correct. But by the time that proof arrived, it was far too late to matter for anything except history. The broader lesson of the Sherman evaluation extends beyond the specific context of World War II. It speaks to the nature of modern industrial warfare, where victory is determined as much in factories and logistics networks as on battlefields. It demonstrates that technological sophistication without industrial capacity is merely theoretical superiority, and it reveals how institutional cultures and doctrinal assumptions can prevent military establishments from recognizing uncomfortable truths until those truths become catastrophically obvious. The Sherman was not the best tank of World War II by most technical measures, but it was good enough, and there were enough of them, and they could be kept running in combat conditions far from home, and that combination proved decisive. The Japanese engineers who examined the captured Sherman understood this. They measured it, tested it, documented it, and reported it. And then they watched as the war ground on toward its inevitable conclusion, knowing that what they had discovered in that test yard in Yokohama was proof of a defeat that had been determined long before the first shot was fired. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.